So let's work with the homogeneous equation that we just introduced. And so we can observe a very important property that we are stating here, that if y1 and y2 are two solutions of the linear differential equation Ly equal to 0, then a combination of y1 and y2 involving arbitrary constants c1 and c2 is also a solution. And so y, which is a linear combination of two known solutions, also solves the original differential equation. This is a very useful statement. It may seem obvious. Let's verify it, and then we will see that certain important consequences will follow from this. So how do we prove such a thing? It's actually very simple. We just have to simply try it out. The proposition that a linear combination of y1 and y2 involving these two arbitrary constants c1 and c2 is also a solution. So let's substitute, let's evaluate what is needed to verify whether this is true or not. And so we need to calculate the first derivative and the second derivative. And so taking the first derivative of this expression simply gets the derivatives acting on y1 and y2. So we have y1 prime and y2 prime, and then the second derivative has second derivatives on y1 and y2. And so we now have the expressions for y1 prime and y double prime, y prime and y double prime, and we can substitute these in the differential equation. So the differential equation was this operator L acting on y, and so y is c1 y1 plus c2 y2. We substitute that, and remember that this operator is made up of the second derivative, some function times first derivative, and a third function times the value y itself. And so we carry out that algebra, we substitute this, and you can manipulate this on a piece of paper, and you can see that rearranging this expression, we will very quickly see that this is equal to c1 times L of y1 plus c2 times L of y2. And since L of y1 is equal to 0, that is the definition that y1 satisfies the differential equation, and likewise L of y2 is equal to 0 because that also satisfies the differential equation. Therefore, for arbitrary constants c1 and c2, this expression is always equal to 0, which means that this composition with arbitrary constants also satisfies the differential equation. So far we just verified that linear combination of two solutions y1 and y2 is also a solution to the differential equation. So you may ask, what about initial conditions? We haven't talked about initial conditions. And so let's specify some initial conditions. And so if we specify the following initial condition, that y at t0 is equal to some given value y0, and the slope y prime at t0 is given by some value y0 prime, we can now try to satisfy these two initial conditions. And so note that y is this linear combination equal to y0 is given, and y prime, which is equal to this, as we had seen by simple derivation, is equal to y0 prime. These two numbers are given. And so if you look at what we have here, we have this equation and that equation. If you think about these as equations for c1 and c2, these are two linear equations involving the two unknowns c1 and c2. So we have two linear equations and two unknowns, and so it's very straightforward to solve. Of course, we can algebraically solve it by combining the second equation with the first and eliminate one of the variables and find, say, c1, and then substitute that back and get c2. And of course, this can be done very compactly. You may recall from your high school algebra a method called Kramer's rule, which can be directly applied to the system of equations. And so using Kramer's rule, we can write down the solution in this explicit form, that the constant c1 is given by the ratio of these two determinants. The numerator is the determinant where in the first column here we have put the right hand side that was given. The second column here is made up of y2 and y2 prime evaluated at t0. In the denominator, we can think of this determinant in the following way. We write y1 and y2 evaluated at t0, and in the second row we write y1 prime at t0 and y2 prime at t0. Well, why is this determinant showing up? Is because if you look at this equation, the determinant associated with the matrix here, if we were to write the left hand side in terms of a matrix times the constants c1 and c2, the two unknowns, we think of them as a vector, we will have this matrix y1, y2, y1 prime, y2 prime matrix times c1, c2 as the vector, the matrix vector product. And so the determinant of that matrix is naturally showing up here in the denominator. Likewise, C2 is given by this, where in the denominator we have the same matrix. And so this matrix plays a very important role. That matrix is the matrix of the denominator, is the matrix appearing in the denominator. And we are giving it a label, W, which depends on y1 and y2, is this determinant, as we saw before. And if we expand it out, we will see that it is y1 times y2 prime, both evaluated at t0, that's the first term, and minus the product associated with these terms. So y1 prime times y2 with a minus sign. So this determinant appears in the denominator, and clearly if this determinant is non-zero, then we can solve the system. We can find the values of C1 and C2 which allow us to satisfy the initial condition. This determinant has a very special name. It was discovered by a mathematician named Wronskian, and so it's called Wronskian, or we can call it the Wronskian determinant, and this will play an important role in our discussion.